Okay, welcome back. So let's begin. Struct. So we introduced vectors in the last lesson. And a vector is going to be an aggregate of elements or a collection of aggregate elements. It's a container that stores elements of the same type. A struct is going to be an aggregate of element of nearly arbitrary types. For instance, let's look at a declaration of this new type, this user-defined type that I'll be able to use within my applications. Struct contact. So I'm assuming, back to the silly phone book example, that opposed to mapping maybe a string to some sort of number, I want to have a concrete representation of the people whose numbers and contact information I'd like to store. So in this case, I'm establishing that my struct is going to have 4 fields. It's going to have the ability to store one string value, which I'll use to house the first name of, say, the person who I'd like to represent, another string to store that last name of that person. In addition to this, a long to store the phone number, again, using long over int, so that we're able to actually represent a full phone number. And then another string for the email. Notice that the definition of this new type is terminated with a semicolon. This right here is no mistake. Make sure you include it anytime you are defining a new type. So at this point, once we've hit that semicolon, a new type is available for use in our program. It's called contact, and it's going to consist of these items that you might store for an individual as an entry in an address book. So using that same type definition here, that struct contact, how do we access the individual fields? Well, the first thing that we're going to want to do is simply declare a new contact. I'm going to give it the name person here. Notice here that this declaration looks no different than any of the other declarations you've encountered to this point. It's just the type of the object we're creating is a contact. If we wanted to create an int, it would have been int I or whatever here, contact person. Okay. So these different fields, or the things that contact stores, are going to be known as the data members of this type. So contact has 4 data members. To access those data members, we're going to use the dot operator. So we'd say person dot first name to access the first name field. Likewise, if we wanted to access the person's last name, it's just person.last name. That's the name of the field. And I can go ahead and assign to it or get the value. In both these examples here, I'm assigning a value to those fields. First name at the end of this statement will take on the string value of Michael. Last name after this statement will take on the value of Nowak. Person.phone number will take on the value here, which is, again, my office phone number. And finally, the email will take on this value that I'm assigning to it. All of this is assignment, though. At this point, once we ran over that, contact person's values are all, well, they're going to be the 0 value of the string type. So each of the string fields is going to be essentially the empty string. The value of long is going to take on an undefined value. So the question is, well, how can we actually initialize objects of the type contact? Similar to how this user-defined type or library type standard library string is seemingly able to give first name, last name, and email some sort of 0 value. Well, we can initialize objects of type contact using uniform initialization. We'll get into how this works, but when we get into classes, we'll see that a better way to go about this and more clear way is going to be to actually use constructors. But we haven't got into that yet, so we're going to work with what we have. So to use uniform initialization, I'm simply going to provide the values for each field in the order that they're declared in the actual type as a list within these within these brace notations. So in this case, contact persons fields are going to be initialized, actual true initialization. They're going to take on from this, the point of declaration forward. First name will have Michael, last name will have Nowak, phone number will have my office phone number, email will have my email. Everything is initialized. The objects fields start out with well-defined values. So how's this work? Again, it's the list here, the initialization list here has to follow the same order as how those fields, the order of declaration of those fields within the actual type definition. So here, Michael will be used to initialize first name. Nowak will be used to initialize the last name. The phone number here, used to initialize phone number. And finally, the email will be used to initialize the field email. The data members of the object being constructed, again, to emphasize this, are initialized in order with the items provided to it within our initialization list. And again, this is satisfactory for right now. We'll get into better ways of initialize objects of user-defined types in the future. But right now, we're just looking for a way to aggregate types of objects that are homogeneous together under one roof. So objects of structure types, so those that are declared within this type contact or any other type that you've defined within your program, can be passed as arguments to functions that can be assigned, and they can also be returned as the result of a function. So we can initialize them using the initializer syntax shown on the previous page. We can assign to them, update their values using the dot notation. So we could also pass these objects as arguments to a function. So we could have a function that does some sort of operation on objects of contact type. And we could also return objects of this type from a function. However, any user-defined type can only do what we've defined it to do. And we've defined essentially nothing at this point. And again, we'll get into member functions and other things a little bit later in the course, and even operator overloading. But right now, we have no ability to compare, say, two objects of type contact for equality or inequality, as we have not defined what it means for two types of these objects to be as such. Furthermore, we have not specified what it means to insert objects of these types into a stream. So if you construct a new contact object, this user-defined type, and you attempt to write stdc out, okay, I'm going to insert this object into an output stream. Hopefully I'll see its contents in this terminal window. No, you're going to see a nasty error, which is very kind of cryptic if you haven't encountered it before. Right now, the only way that you know to output the contents of this object would be to just go through each of the members using dot notation. So going through the motions and actually writing them out. We will get to a point in this semester where we will introduce how we can define what it means to insert an object of user-defined type directly into an output stream. But for now, we're going to kind of resort to this dot notation and doing it, I guess you could say, longhand. Again, here's the, we're attempting to test for equality. In the second example here, I have declared somewhere person and person two. I know very poorly poor names. They're not very descriptive, but okay, anywho, they are two contact objects. And if we attempt to test them for equality, the error that we'd see is going to be invalid operands to binary expression. There's no, this operation for the binary expression, for the binary operator that we use for equality has not been defined for objects of contact on the left-hand side and contact on the right-hand side. And again, in due time, you'll learn how to define all of this. But for now, you'd have to actually compare the fields individually, because the test of equality for two strings has been defined for the string type long that's within the implementation. So that's kind of an introduction to structs. We'll get into writing structs in C++ here in the next. Even though we've kind of showed an example, we'll get into kind of the style and everything else.